Huge fan. Well, that's it. Thank you.
Thank you so much, Professor James McClurkin.
Great job. I'm really glad we got to do the demo.
Okay, so very briefly, before we go to lunch, someone asked a moment ago, where can I donate online? I have the answer. It is www.singinst.org/donate. So that's singinst, like Singularity Institute, but short, .org/donate. One more time, www.singinst.org/donate. We are coming back from lunch at 2:30, and Stephen Wolfram will be up first. Your lunch is out into the main hall and just on the right, same place that breakfast was served. So you'll go through a buffet line, and you'll be back here at 2:30, and we'll see you then. Welcome back. Welcome back. So you've probably noticed that we're starting after lunch here at 2:30 instead of 2 o'clock, which was originally on the program. Fortunately, we had an hour break planned for the afternoon, so we're going to chop that down to 30 minutes. At least that's the plan for now. Maybe it'll get squeezed even to 15 later. But we're going to nominally say that that's going to be 30 minutes, and we should be able to end right on time. So to start after lunch, Stephen Wolfram is here. He is the founder and CEO of Wolfram Research. He earned a PhD in theoretical physics from Caltech at the age of 20, and he received one of the first MacArthur Fellowships in 1981 at the age of 21. Since then, he has launched 3 related revolutions. In 1988, he introduced the Mathematica computation system, which Steve Jobs helped him name. Mathematica has since revolutionized technical computation and has been responsible for countless advances over the past 2 decades. In 2002, he published A New Kind of Science, an empirical study of simple programs that generate tremendous complexity. Insights from the book have led to breakthroughs in scientific modeling in several domains. Most recently, in 2009, he launched the Wolfram Alpha Computational Knowledge Engine, an ambitious project to make the world's knowledge computable and accessible to everyone. Wolfram Alpha is already used in Microsoft's Bing search engine and also in Apple's new Siri digital assistant, which is included only in the latest iPhone. Today, he will discuss his long-term expectations for technology and the human condition. Please welcome Stephen Wolfram.
Thank you. Okay, well, what I wanted to do here was, at least as far as I'm concerned, have some fun and talk about the future, which is something that's kind of recreational for me, because what I normally do is to work sort of in the trenches, just trying to actually build the future kind of one brick at a time, or at least one big project at a time. So I've been doing that now for a bit more than 30 years, and I guess I've built a fairly tall tower from which it's possible to do and see, I think, some pretty interesting things. Actually, things are moving quite fast right now. Example from yesterday, here's an iPhone 4S. If you press the button to call up Siri, you can talk to it and you can ask it all kinds of questions, and quite often it'll compute answers, kind of Star Trek computer style, using our Wolfram Alpha knowledge engine. Well, there's a lot to say about Wolfram Alpha, about how it relates to artificial intelligence, about the whole idea of computational knowledge, what it means for the future, and so on. But let me start off at sort of a more conceptual level. I wanted to sort of talk about worldviews. Let's stop doing that. Okay. So, you know, a lot of the way we tend to think about the world, and particularly about science and technology, is sort of very Newtonian, very Galilean. I mean, it's a great tradition that's done amazing things over the past 300 years, all sort of rooted in physics, with sort of math as a kind of aspiration for how to describe things. In a sense, it all got started with one surprising discovery that got made in 1608 when Galileo turned his telescope to the sky and saw for the first time the moons of Jupiter, and began to realize that there really could be this sort of universal physics that applies everywhere, and from which we could sort of ultimately build this whole edifice that is modern exact science and technology. Well, I myself happened to start out early in life as a physicist, and so I was very much steeped in this whole physics-math worldview. But as I studied different kinds of things, particularly ones where there was sort of obvious complexity in the behavior of a system, I kept on finding cases where I couldn't make too much progress with that. And I got to wondering whether there was sort of something fundamental that had to change. Well, one of the big issues was this. When we look at some system in nature, how do we think about the mechanism for that system? So the big innovation of Galileo and Newton and friends was to have the idea of using mathematics to describe this mechanism, so that we get all these equations and math and calculus for the systems we study in science or we build in technology. But sort of here's the question. Is that the only mechanism that nature can be using? Well, what I realized is that it's certainly possible that there are other mechanisms, rules that are precise but that aren't captured by, for example, our standard mathematics. And the nice thing is that in our times, we have a way to think about those more general rules. They're like programs. Well, when we think of programs, we usually think of these big things that we build for very specific purposes. But what about sort of little tiny programs, maybe just one line of code long or something like that? You might have thought, as I certainly did, that programs like that would always be trivial. They'd never do anything interesting. But one day, nearly 30 years ago now, I decided to actually test that idea, and I took sort of my analog of a telescope, a computer, and pointed it not at the sky, but at sort of the abstract computational universe of possible programs. So this is one of the things that I saw. So each one of these pictures is the result of running a different simple program. And you can see there are all kinds of different things that happen, most of them quite trivial. But if you look carefully, you'll see something quite remarkable. That the 30th one of these is the thing I call Rule 30. And here's what it does. So you start it from just one black cell at the top, and then you use that little rule at the bottom. It looks like a trivial rule, but here the result of running that rule is you get all this stuff. Complex, in some ways random, no sign that it came from that little simple rule at the bottom. Well, when I first saw this, I didn't actually believe it. I thought that somehow there must be some regularity, some way to decode what we're seeing. I mean, in our usual intuition, we have the idea that to make something complex, we have to go to lots of effort. It can't just be to take some tiny little rule like that. But I suppose this was my own personal little sort of Galileo moment, the beginning of, for me, of a new worldview with new and different intuition informed by what I'd seen sort of out there in the computational universe. Well, over the years since I discovered Rule 30, I've gradually been understanding more and more about the worldview that it implies. And I feel very slow because there's sort of many layers to understand. But it's been tremendously exciting, and the more I understand, the more important I think it is for understanding the world and for building the future. And of course, there's some pretty interesting spin-offs that I'll explain a little bit more about, like Wolfram Alpha, for example. Well, so we have this new kind of science that's based on exploring the computational universe of possible programs. What does it mean? So here's one immediate thing. There's a really basic issue in science that I guess has been around pretty much forever. It's this question: how is it that nature manages to make all the complicated stuff that it does? You know, it's sort of embarrassing. I mean, if you show someone two objects, one of them's an artifact, one of them's a natural system, it's a good heuristic that the one that looks simpler is the artifact. With all that we've achieved in our civilization and so on, nature still has some secret that lets it sort of effortlessly create stuff that's more complex than we can build. Well, I think we now know how this works. I think Rule 30 is a great example. It's just that when we build stuff, we operate according to fairly narrow kinds of rules that let our current science and technology let us understand what's going on. But nature is under no such constraint. It just uses all kinds of rules from sort of around the computational universe. And that means that, like in Rule 30, it can sort of effortlessly produce all the complexity that it wants. Well, after I started building Mathematica as my kind of computational power tool, I spent about a decade using it to try to understand the implications of this for all kinds of science and so on. And indeed, there are lots of long-standing problems in physics and biology and elsewhere in science that one starts to be able to crack, which is very exciting. But, okay, it's one thing to understand something about how nature works. How about building stuff for ourselves? How about technology? Well, there's something very interesting here. You see, mostly in technology, what we do is to try to construct stuff step by step, always sort of making sure we can foresee what's going to happen. That's the traditional approach in engineering. But once we've seen what's out there in the computational universe, we realize there's actually another possibility. We can just mine things from the computational universe. You know, in a sense, the whole idea of technology is to take what exists in the world and harness it for human purposes. And that's what happens when we take materials that we find out there, whether it's magnets or liquid crystals, whatever, and then we find technological uses for them. Well, it's the same in the computational universe. Out there, there are things like Rule 30 that behave in remarkable ways and that we can sort of effectively harvest to make our technology. Like, Rule 30 is a great randomness generator. Another rule might be great for some kind of network routing or image analysis or whatever. You know, as we've developed Mathematica, for example, and even more so Wolfram Alpha, we've increasingly been using this idea, not creating technology by explicit engineering of the kind we normally think of, but instead mining it from the computational universe. In effect, searching zillions of possible simple programs to find ones that turn out to be useful to us. Now, once we have these programs, there's no guarantee we can readily understand how they work. We have some way of testing that what they do is what we want, but their operation can be as mysterious and look as complex as what we often see in nature. So it's been interesting in the last few years watching the advance of this idea of mining technology from the computational universe. It's not too easy to trace everything that's happening, but in more and more places it's catching on. And my guess is that in time, this approach, this sort of new kind of technology, will come to dwarf everything produced by all that step-by-step traditional engineering. You know, it's actually not just technology that's involved. Like, here's an experiment we did a few years ago in the artistic domain, scanning through lots of rules in the computational universe to find ones that create music in different styles. In a sense, using the fact that there is an underlying rule so that there's a kind of logic to each piece, but yet as a result of kind of Rule 30 type phenomenon, there's complexity and richness that we as humans respond to. And actually, you know, it's funny. I had thought that a big thing about humans is that they're the creative ones. Computers aren't. But actually, I keep on hearing from composers and so on that they like this site because it gives them ideas, inspirations for pieces. So out there in the computational universe, there's in effect a whole sort of seething world of creativity ready for us to tap. And, you know, it's interesting how this sort of changes the economics of things. I mean, mining the computational universe makes creativity cheap. It means that we don't have to mass produce, we can mass customize. We can sort of invent on the fly on a mass scale. And actually, there are things coming, for example, in Wolfram Alpha, that will really make very direct use of this. Well, okay, I wanted to go back to kind of worldviews a bit, because there's some development of my worldview that I have to explain to talk more about things that I'm expecting might happen in the future. So, okay, how can we understand this sort of remarkable phenomenon that we see in Rule 30 and in lots and lots of other places? Another example. So, from my explorations in the computational universe, I came up with a hypothesis that I call the principle of computational equivalence. So let me explain it a bit. When we have a system like Rule 30, or like the system here, like something in nature, we can think of it as doing a computation. In effect, we feed in some input at the beginning, then it grinds around, and eventually out comes some output. Then the question is, how sophisticated is that computation? Well, we might have thought that as we make the underlying rules for a system more complicated, the computations it ends up doing would somehow be progressively more sophisticated. But here's the big claim of the principle of computational equivalence, that isn't true. Instead, after one passes a pretty low threshold, and one has a system that isn't obviously simple in its behavior, one immediately ends up with a system that's doing a computation that's as sophisticated as anything. So what that means is that all these different systems, whether it's Rule 30 or whether it's a fancy computer or a brain, they're all effectively just doing computations that have the same level of sophistication. Well, okay, so there's an immediate prediction then from the principle of computational equivalence. There's this idea of universal computation. It's really the idea that launched the whole computer revolution due to Alan Turing and friends. You might have thought that any time you want to do a different kind of computation, you need a different system, completely different system. But the point of universal computation is that you can have a single universal machine that can be programmed to do any kind of computation. And that's what makes software possible, and that's the foundation for essentially all computer technology today. But okay, the principle of computational equivalence has many implications, but one of them relates to universal computation. It says that not only is it possible to construct a universal computer, but actually it's easy. In fact, pretty much any system whose behavior isn't obviously simple will manage to do universal computation. Well, one can test that. Just look, for example, at these simple programs like Rule 30 and see if they're universal. We don't yet know about Rule 30 in particular, but we do know, for example, that a program very much like it, Rule 110, is universal. A few years ago, we found that even among Turing machines, the very simplest one that shows not obviously simple behavior, but still has a very simple rule, is also universal. Now, we might have thought that to build something as sophisticated as a universal computer, we'd have to build up all kinds of stuff. We'd in effect have to have this whole civilization that figures out all of these different kinds of things. But actually, what the principle of computational equivalence says, and what we found out is true, is that actually out there in the computational universe, it's really easy to find universal computation. It's not a rare and special thing, it's ubiquitous. And for example, it'd be easy to mine from the computational universe, say for the particular case of practical importance of making molecular computers or something. Well, okay, the principle of computational equivalence has other implications too that are pretty important. One of them is what I call computational irreducibility. See, a big idea of traditional exact science is that the systems we see in nature are computationally reducible. We look at those systems, say an idealized Earth orbiting an idealized sun, and we can, with sort of all our mathematical and calculational prowess, we can immediately predict what those systems are going to do. We don't have to trace every orbit, say. We can just plug a number into a formula and immediately get a result, using the fact that the system itself is computationally reducible. Well, it turns out that in the computational universe, one finds that lots of systems aren't computationally reducible. Instead, they're irreducible. There's no way to work out what they will do in any reduced way. There's no choice but just to trace each step and see what happens. It's actually pretty easy to see why this has to happen, given the principle of computational equivalence. We've always had kind of an idealization in science that systems we study are somehow computationally much simpler than us as observers that study them. But now the principle of computational equivalence says that that isn't true, because it says that a little system like Rule 30 can be just as computationally sophisticated as us with our brains and computers and so on. And that's why it's computationally irreducible, and by the way, also why its behavior seems to us so complex. Well, computational irreducibility has all sorts of implications for the limits of science and knowledge. At a practical level, it makes it clear how important simulation is and how important it is to have sort of the simplest possible models for things. And for example, a philosophical level, I think it finally gives us an explanation for how there can be both free will and determinism. Things are determined, but to figure them out requires an irreducibly large computation. But okay, so the principle of computational equivalence has another implication that relates to intelligence. There are various concepts, like life, for example, that always seem a bit elusive. I mean, it's pretty easy to tell what's alive and what's not here on Earth. But all life shares a common history here and has all sorts of detailed features in common, like cell membranes and RNA and so on. But what's the abstract definition of life? Well, there are various candidates, but realistically they all fail. And either we have to fall back on the shared history definition, or we have to just say, in effect, that what we need is a certain degree of computational sophistication. Same thing with intelligence. We sort of know historically what human-like intelligence is about, and we don't have a clear abstract definition, sort of independent of that history, and I think ultimately there just isn't one. In fact, it's sort of a consequence of the principle of computational equivalence that we can't make one, and that all sorts of systems are ultimately equivalent in this way. I mean, you know, there are expressions like, the weather has a mind of its own. And one might have thought that that was just some very primitive, animistic point of view of the world. But what the principle of computational equivalence suggests is that, in fact, there is a fundamental equivalence between what's going on in, for example, the fluid turbulence in the atmosphere and things like the pattern of neuron firings in our brains. And you know, this type of issue gets cast into a more definite form when one starts, for example, thinking about extraterrestrial intelligence. I mean, if we see some sophisticated signal coming from the cosmos, does it necessarily follow that it needed some whole development of an intelligent civilization to make it? Or could it instead just come from a physical process that operates according to simple underlying rules? Well, our usual intuition would be that if we see something sophisticated, it must have a sophisticated cause. But from what we've discovered in the computational universe and encapsulated in the principle of computational equivalence, that's not the case. And when we see, you know, those little glitches in signals from a pulsar or something, we can't really say they're not associated with something like intelligence. Well, of course, historically, things like this were often plenty confusing. I mean, like Tesla's radio signals from Mars that turned out to be modes of the ionosphere and so on. And it sort of gets even worse. I mean, let's for a moment imagine the distant future where technology discovered from the computational universe is widely used, and all our processes of human thinking and so on are implemented at a molecular scale and by motions of electrons in some block of some material or another. Now imagine we find that block lying around somewhere, and we ask whether what it's doing is intelligent. Well, I don't think that's really a meaningful question as such. And in fact, I don't think there'll ever be a fundamental distinction between the processes that go on in that block and in a pretty generic block of material with electrons whizzing around. As we learn from the principle of computational equivalence, at a fundamental level, they're both doing the same kind of thing. Of course, at the level of details, there can be a huge distinction. One of them can have an elaborate history that's all about the details of our evolution and our civilization, and the other one doesn't. As I'll talk about in a bit, this is sort of all bound up with issues of purpose and so on. But at the level of just looking at these blocks of material without the details of history, there's no fundamental distinction, I think. Well, needless to say, this sort of realization also has implications for artificial intelligence. You know, when I was younger, I used to think that there'd be some great idea, some core breakthrough that would suddenly give us artificial intelligence. But what I've gradually realized, especially through the principle of computational equivalence, is that that's just not how it'll work. Because in a sense, all this intelligence that we're trying to make is ultimately, at an abstract level, just computation. That might sound very abstract and philosophical, but at least for me, it's had a big practical consequence. I mean, when I was a kid, I was really interested in the problem of sort of taking the world's knowledge and setting it up so that it would be possible to sort of automatically ask questions on the basis of it. Seemed like a hard problem, because to solve it, it seemed like one would have to solve the general problem of artificial intelligence. But after I'd come up with the principle of computational equivalence, I gradually realized that that really wasn't true, and that in a sense, all one had to do was computation. Well, at a personal level, I had this great system for doing computation, Mathematica, with a language that could very efficiently represent all this abstract stuff, and a whole sort of giant web of algorithms covering pretty much sort of every fundamental area. And so I thought, okay, maybe it isn't so impossible or crazy to actually try to build a system that will make the world's knowledge computable. That was how I came to start off building Wolfram Alpha. I have to say that I'm still often surprised that Wolfram Alpha is actually possible as a practical matter at this point in history. I mean, it's an incredibly complicated technological object, but I'm happy to say that the big discovery of the last couple of years is that it actually is possible to make this work. And it's steadily expanding sort of domain by domain, in effect sort of automating the process of delivering kind of expert-level knowledge on all kinds of things. And making it so that if there's something that could be figured out by an expert from the knowledge that our civilization has accumulated, then Wolfram Alpha can automatically figure it out. So from the point of view of sort of democratizing knowledge, it's pretty exciting, and it's clear that it's already leading to some pretty interesting things. Inside, though, it's definitely a strange kind of object. I mean, it starts off from sort of all sorts of sources of data that at first are just raw data, but the real work is in making that data computable, making it so that one isn't just looking things up, but instead one's able to figure things out from the data. In that process, a big piece is that one has to implement all the various methods and models and algorithms that have been developed across science and all the other areas. And one has to capture the expertise of actual human experts. They're always needed. So then the result is that one can compute all kinds of things. Then the challenge is to be able to say what to compute. And the only realistic way to do that is to be able to understand actual human language, or actually the strange utterances that people enter in various ways to Wolfram Alpha. And somewhat to my surprise, using a bunch of thinking from New Kind of Science, it's turned out that it's actually possible to do a pretty good job of this. In effect, turning human utterances that in the textual domain often seem like they're rather close to raw human thoughts into a systematic symbolic internal representation from which one can compute answers and generate all those elaborate reports and so on that you see in Wolfram Alpha. Well, it's kind of interesting what happens in the actuality of Wolfram Alpha. People are always asking it new things, asking it to compute answers to their specific situation. The web has lots of stuff in it, but searching it is sort of quite a different proposition, because all you're ever doing is looking at things people happen to have written down. What Wolfram Alpha is doing is actually figuring out new specific things. In some ways, it's achieving all sorts of things people have said in the past are characteristic of an artificial intelligence. But it's interesting the extent to which it's not like a human intelligence. I mean, think, for example, about how it solves some physics problem. It could do it like a human, kind of reasoning through to an answer, kind of in the sort of medieval natural philosophy kind of style. But instead, what it does is to make use of the last 300 or so years of science. From an AI kind of point of view, it kind of just cheats. It just sets up the equations, blasts through to the answer. It's really not trying to emulate some kind of human-like intelligence. Rather, it's trying to be the structure that all the human-like intelligence can build to do what it does as efficiently as possible. It's sort of not trying to be a bird, it's trying to be an airplane. Well, so now I've explained a little bit about my worldview and a bit about how it's led me to some very practical things like Wolfram Alpha. Let me talk now a little bit about what I think it tells us about the future. I'll talk both about the fairly near-term future and about the much more distant future. I don't talk very much about the future usually. I find it a bit weird because I like to just deliver stuff, not talk about what could be delivered. But I certainly think a lot about the future myself, and I've ended up with a whole inventory of sort of major projects that I think can be done in the future. But the challenge for me is sort of to wait for the right year or the right decade to actually do them. I always try to remember what I predicted about the future in the past and then check later whether I got it right. Sometimes it's kind of depressing. I mean, I was recently reminded in 1987, I worked with some team of students we won a competition about predicting the personal computer of the year 2000. And at the time, it seemed pretty obvious how some things were going to play out. And looking recently at what we said, it's depressing how accurate it was. I mean, touchscreen tablet with various characteristics and uses and so on. I guess there are some things that sort of that are progressing, pretty much progressing in sort of straight lines like that, where nothing is terribly surprising. I must say, personally, I always much prefer to build what I think of as kind of alien artifacts, stuff that people didn't even imagine was possible until it arrives. But anyway, what can we see in kind of straight lines from where we are? Well, first, data and computation are obviously going to become more and more ubiquitous. We'll have sensors and things that give us data on everything. We'll be able to compute more and more from it. It used to be the case that one had to just sort of live one's life from one's wits and what one happened to know about and be able to work out. But then long ago, there were books that started to spread knowledge in a systematic way, and more recently, there started to be algorithms on the web and computational knowledge and all those kinds of things. Actually, we made this poster recently about sort of the advance of systematic knowledge in the world and the ability to compute from it, sort of from the Babylonians to now. And it realized it's been a pretty important driving force in the progress of civilization, sort of gradually getting more systematic and more automated. Well, okay, so at least in my little corner of the world, we have Wolfram Alpha, which takes lots of systematic knowledge and lets one be able to compute answers from it. And as that gets done more and more of what happens in the world will become understandable and predictable. One will routinely know what's going to happen, at least up to the limits of what computational irreducibility allows. Right now, one usually still has to ask for it, explicitly say what one wants to know about. Increasingly, though, the knowledge we need will just be delivered preemptively when and where we need it, with all kinds of interesting new interface technologies that kind of link more and more directly into our senses. There's sort of a big question of knowing what knowledge to deliver, though. And for that, our systems have to know more and more about us, which isn't going to be hard. I mean, informational pack rats like me have been collecting data on themselves for ages. I've got dozens of streams of data, including things like every keystroke I've typed for the past 20 years and stuff like that. But all of this will eventually become completely ubiquitous. We'll all routinely be doing all sorts of personal analytics and judging. From my own experience, we'll quickly learn some interesting things about ourselves from it. But more than that, it'll allow our systems to successfully deliver knowledge to us preemptively. All kinds of detailed issues. Will it be that our systems can systematically sense things because the environment is explicitly tagged, or will the systems have to deduce things indirectly with vision and so on? But the end result is that quite soon we'll have an increasing sort of symbiosis with our computational systems. In fact, in Wolfram Alpha, for example, in just a few short weeks, it'll be able to start taking images and data as well as language-based queries as input, sort of beginning that ramp. And increasingly, our computational systems will be able to predict things, sort of optimize things, communicate things, much more effectively than us humans ever can. But sort of here's a critical point. We can have all this amazing computation, effectively all this amazing intelligence, but the question is, what is it supposed to do? What is its purpose? You know, you look at all these systems in the computational universe, and you see them doing all this amazing stuff they're doing. But what is their purpose? Well, sometimes we can look at a system and say, what that system does is more economically explained by saying it achieves a certain purpose than just that it operates according to a certain mechanism. But ultimately, our description of purposes is a very human thing, and very tied into the thread of history that runs through our civilization. I mean, when the thread of history is broken, it's very hard, even with something like Stonehenge, to know what its purpose was actually supposed to be. And you know, when we look at the future, it's pretty obvious that more and more of our world can be automated at an informational level, at a physical level. One of my pet future projects, for example, that I don't think we're quite ready for yet, is to really turn robotics into a software problem. I sort of imagine some bizarre collection of little tiny identical objects kind of moving around, perhaps sort of Rubik's Cube style, operating a bit like cells in a cellular automaton, a kind of universal mechanical object that configures itself in whatever way it needs. And I'm guessing that this can be done at a molecular level too. And I've actually got some pretty definite ideas from NKS about how to do it. But I don't think that the ambient technology exists yet. There's still a lot of practical infrastructure to be built. Well, when so much can be automated, even, you know, as I mentioned before, sort of creative things, it'll be interesting how economics change. Some things will still be scarce, but so much will, in a sense, be infinitely cheap. Then, of course, there's us humans as biological entities. One question one can ask is how the kind of worldview that I have affects how one thinks about that. I mean, people like me have all this data about their genomes, for example, but how does one sort of build the whole organism from that? What are the kind of architectural principles? Should we imagine that it's kind of like flowcharts or simple systems of chemical equations, where one thing affects another and we can just sort of trace the diagram around? I suspect that in many cases it's more complicated. It's more like what we see all over the computational universe. I mean, lots of cellular automata look so biological in their behavior, and we can now know that we now know lots of detailed examples where we can map systems like cellular automata onto biological systems, whether at a macroscopic scale or a microscopic one. And what we realize is that many aspects of biological systems are operating like simple programs, often with very complex behavior. And that means all those phenomena like computational irreducibility come in. You know, will some tumor-like process in a biological system grow forever or not? That might be like the halting problem for a Turing machine. It might be formally undecidable, and to know what will happen for any finite time, we just have to simulate each step. You know, if one starts thinking about, can start thinking about all sorts of basic questions in medicine. Here's an analogy. Think of a human being as being a bit like a big computer system. System runs just fine for a while, but gradually it builds up more and more cruft. Buffers get full, whatever. And no doubt the system has bugs too, and sometimes those get in the way. Well, eventually the system gets so messed up that it just crashes, it dies. And that's rather like what seems to happen with us humans. And of course, with a computer system, one can just reboot and start again from the same underlying code, very much like the next generation for humans can start again from more or less the same genome. You know, for humans, we have all this medical diagnosis stuff, all these diagnosis codes for particular diseases and so on. We can imagine doing that for computer systems too. You know, diseases of the display subsystem, you know, diseases of memory management, trauma to the I/O system, so on. I think it'd be instructive to really work this through, actually. What I know one will find is that the idea of very specific diseases is not really right. There are all these different shades, things that can't really even just be described by parameters. They have to be really described by algorithms. Well, when we run all the servers for Wolfram Alpha, for example, we have, by the standards of the computer industry, very beautiful Mathematica-powered dashboards showing us kind of the overall health of the different pieces of the system, and it all worked beautifully yesterday as the Siri system turned on and so on. But these things are very coarse, and I think it'll be interesting to see how much more detail we can represent well. I mean, there's a lot of computational irreducibility lurking around. The very phenomenon of bugs is a consequence of computational irreducibility. But the question is, how should one best make a sort of detailed dashboard that allows one to trace the path of problems in a big computer system? It's sort of a model for how we should do this for us humans, sampling all sorts of things with sensors or genomic assays or whatever. Sampling what's happening, then computing to see what consequences things will have. In case of big computer systems, we tend to just use redundancy and parallelism and not to worry too much about individual pieces dying. So we don't yet know much about what we do to go in and do sort of interventions. With humans, we do care about each one, and we want to be able to do that. It's going to be a tough battle with computational irreducibility. No doubt we'll have algorithmic drugs and so on, where molecules can effectively compute what to do inside our bodies. But figuring out the consequences of particular actions will be difficult. That's sort of the lesson of computational irreducibility. But still, I'm quite sure that in time, for all practical purposes, we'll be able to fix our biology and keep things running forever. Actually, I have to say that an intermediate step will surely be various forms of biostasis. I'm always amused at what happens in things in science. Like I remember cloning, where I asked a zillion times why mammalian cloning couldn't be done. And there were always these very detailed arguments. Well, as we know, eventually this kind of weird procedure got invented that made it possible. And I guess, I very strongly suspect that the same kind of thing will happen with cryonics. I'm sure there's nothing fundamentally impossible about it. And right now, it's kind of a weird, non-respectable thing to study, but one day some wacky procedure will be invented that just does it. And it'll immediately change all sorts of attitudes about psychology, about death, and so on. But it's only just one step. I mean, in the end, one way or another, effective human immortality will undoubtedly be achieved, and it'll be the single largest discontinuity in human history. And I wonder what's on the other side, though. I mean, so much of society and human motivation and so on is sort of tied up with mortality. When we have immortality and all sorts of technology, we'll at some level be able to do almost anything. So then the big question is, what will we choose to do? Where will our sort of overarching purpose come from? It's sort of strange how our purposes have evolved over the course of human history. I mean, so much of what we do today in our intellectual world or in virtual worlds or whatever else would seem utterly pointless and purposeless to people from another age. I mean, I think computational irreducibility has something to say here. I think it implies that there at least exists a sort of endless frontier of different purposes that can be built on one another. In a sense, computational irreducibility is also ultimately why history is meaningful. Because if everything was reducible, one would just always be able to jump ahead, and nothing would be achieved by all those steps of history. But even though new purposes and new history can be built, will we choose to do so? Hard to know. Perhaps for all practical purposes, history will end. You know, I have a strange guess about at least part of this. My guess is that when, in a sense, almost anything is possible, there'll be in a sort of almost religious interest, not in the future, but in the past. I mean, perhaps it'll be like the Middle Ages, when it was the ancients who had the wisdom. And instead, in the future, people will seek their purposes by looking at what purposes existed at a time when not everything was yet possible. Perhaps it'll even be our times now that will be of the greatest interest, because we're at that point in history where a lot is, for the first time, really getting recorded, but not everything is possible. It's sort of a big responsibility, perhaps, for our times, if it will define sort of the purposes for all of the future. Perhaps it'll be that way. You know, I talk about everything being possible, but ultimately we are just physical entities governed by the laws of physics. So an obvious question is what those laws ultimately are. And you know, the worldview that I've developed has a lot to say about that too. I mean, ultimately the real question is, if our universe is governed by definite rules, it must in effect be one of those programs that's out there in the computational universe that is that rule. Now, it could be a huge program. It could be that the universe is run by a giant operating system. Or it could be a tiny program, just a few lines of code. In the past, it would have seemed inconceivable that all the richness of our universe could be generated just by a few simple lines of code. But once we've seen what's possible and what's out there in the computational universe, it's a whole different story. Let me not get into this in too much detail now, but it's a big topic. But suffice it to say that if the universe can really be represented by a few simple lines of code, then it's inevitable that that code must operate at a very low level, below, for example, our current notions of space or time or quantum mechanics or whatever. Well, I don't think we know a priori whether our universe is actually a simple program. Of course, we know it's not as complicated as it could be, because after all, there is order in the universe. But we don't know how simple it might be. And I suppose it seems very kind of non-Copernican to imagine that our universe happens to be one of the special simple ones. But still, if it is simple, we should be able to find it just by searching the computational universe of possible universes. And if it's out there to be found, it seems to me kind of embarrassing that we wouldn't at least try to look for it. Which is why, when I'm not distracted by fascinating technology I like to build, I've worked a lot on doing that kind of search. Actually, I had thought that to get anywhere interesting, I'd have to search through billions of candidate universes to find one that was even vaguely plausible. But I have to say, at the front lines of the universe hunt, the easy part is rejecting universes that are obviously not ours. Universes that have no notion of time, or an infinite number of dimensions of space, or no notion of causality, or whatever else. But here's the surprising thing that I found. Even in the first 1,000 universes or so, there are ones that aren't obviously not our universe. So you run them on a computer, you get billions of little microscopic nodes or whatever, and the model universe is blobbing around, but is it our universe or not? Well, computational irreducibility bites us once again here, because it tells us that we might have to simulate all the actual steps in the universe to find out the answer to that question. Well, in practice, I'm hopeful that there are enough pockets of computational reducibility that we'll be able to get a foothold in comparing with the laws of the universe that we know. When one's dealing with sufficiently simple models, it's also worth realizing there are no knobs to turn. You either have something that's dead right or dead wrong. I don't know how it will all come out. I think it's far from impossible that in a limited time we'll effectively hold in our hands a little program and be able to say, this is our universe in every precise detail. Just run it and you'll grow our universe and everything that happens in it. Well, then we'll be asking, why is it this program and not another? And that'll be an interesting and strange question, which I suspect might be resolved, as such questions so often are, by realizing that actually it's not quite a meaningful question. Because perhaps in some principle beyond the principle of computational equivalence, maybe all non-trivial universes in some fundamental sense are precisely equivalent when viewed by entities inside them. I'm not sure. But if we do manage to find the fundamental theory, the fundamental program for the universe, it'll kind of ground our sense of what's possible. It won't be easy because of computational irreducibility to answer everything. It might even be, for example, undecidable whether something like warp drive is ever possible. But we'll have at least gotten to the edge of science in a certain direction. Well, let's see. I think I probably ran out of time long ago, but I should probably wrap up here. So all these things that I've been talking about kind of started with this one little experiment with Rule 30, sort of a crack for me in everything that I thought I knew about science. That's gradually widened to give kind of a whole worldview that I've tried to explain a little bit here, that I think is going to be sort of increasingly important in understanding and defining our future. So, thanks very much. I hope we have time for some questions.
We've got about 5 minutes for questions.
Great.
First one over here on the right. Yes, on the aisle.
I'm sorry. There's a microphone, so
This is.
I think you have to. Nobody will hear you without a microphone. Please go ahead.
My name's Rick Schwall, and I'm with Saving Humanity from Homo sapiens. I almost can't phrase my question, so I'll put it this way. Here you've got a diagram that's the output of a simple program. Now I say, one of those white spots, I want to put 3 little spots inside it. Now, find the program that does that. Is it likely to be a simple program?
So, if you say, of all possible pictures that you could generate, is every possible picture generated by a simple program? The answer is no. There's a certain set of pictures that can be generated by simple programs. That's kind of just an easy question of counting, that the number of simple programs is small compared to the number of complete pictures. That's why it's sort of contentful to say that some particular process is governed by a simple program and another is not. So I'm not quite sure what... the whole point is that if, for example, our universe is governed by a simple program, it does all kinds of complicated things, but it does a definite set of complicated things governed by that particular simple program. It would take another, it's not that it does all possible kinds of things, it does a particular set of things governed by a particular program.
Any plans to expand Wolfram Alpha in terms of pair-consistent logics and quantum computing?
Well, let's see. I mean, you can... Let's see. You can go ask Wolfram Alpha. Let's see. I mean, if I start saying P and Q or not R or something, it'll happily, hopefully, if it's connected and everything, it'll happily work out all sorts of wonderful things about logic. Any kind of logical model that... it's interesting, actually. Wolfram Alpha, living on top of Mathematica, has sort of the finest logic capabilities you can imagine and fine capabilities to prove theorems and do inferences and all these kinds of things. It's actually a little depressing how rarely that kind of thing is actually important in practical answering of questions. It's much more, it absolutely pales in comparison with the achievements of sort of the more mathematically and algorithmically oriented areas of science. I mean, I suppose in the Middle Ages, logic and math were kind of neck and neck. Math won out, logic trailed behind, and that seems to be reflected in kind of where, how much it's useful or not. In terms of things like non-standard logics, quantum logics, and so on, I think you can ask Wolfram Alpha all kinds of things about quantum mechanics and quantum computing even a bit, and it'll tell you all kinds of things. It just runs on plain old classical computers, though. My own guess, I happen to have been involved with quantum computing since it didn't exist back in probably 1980 or so. And I have to say, I've always been a bit of a skeptic. I've always thought that these problems of measurement that exist in sort of quantum mechanics are that kind of you can't really address without getting into quantum field theory and so on, and where sort of these concepts of quantum computing don't really quite make it over to quantum field theory because that's a much more complicated formalism and so on. I've always kind of been a bit skeptical about whether quantum computing is all that it's cracked up to be. In fact, my most cynical guess has been that victory will inevitably be declared in quantum computing, because what will actually happen is that people will think of photons and optics and interference and so on as being something a bit quantum-like, and that is a very useful direction for computing. But that's sort of just a cynical view. We have another...
Yeah, unfortunately, we are out of time for questions.
Okay, let's just do one here.
Yeah.
Since he's been waiting...
Thank you. I think I raised my hand first. I look at, I've made a living of modeling real-world systems, and I look at you talking about computational equivalence, and I try and put these two together, and I respectfully say to you that the computational equivalence is neither necessary or sufficient, because when you get down to an answer, you ask, does it preserve the laws of conservation of energy? And it doesn't necessarily so. It doesn't so unless you've proved it, and I don't believe you've proved it.
Well, no, wait a minute. Things like conservation of energy, that's a very specific kind of mathematical issue about models.
90% of our physical world.
Sure. But I mean, any one of these kinds of things that you pluck from the computational universe, for example, you can ask, are they reversible? Do they satisfy conservation laws? Most of them aren't reversible. Most of them don't satisfy conservation laws. Some fraction do.
It does.
What's that?
At the increment of it happening physically, it does. Otherwise,
right,
you can't
so
get the
for some
physical
kinds of
behavior.
systems, if you want to study, so what's actually happened in practice is that people use sort of things that you can find in the computational universe as raw material for making models of things. And in the course of science, one of the slowest processes is the invention of new models. If you look at the literature of science, there's some set of named models, and they're actually a fairly small set. And most of science consists in working on these same models over and over again.
Sure, they're easy.
Right. One of the things that's nice about what's happened with sort of exploring the computational universe is there's this kind of inexhaustible supply of sort of innovative new models. And you can ask which kinds of models turn out to be relevant. Is it important? Is the most important aspect that they have some conservation law, that they have reversibility, something like that? In some areas it is. In many areas it's not. In social science, it doesn't make any difference. The notion of reversibility or conservation, irrelevant for social science. When you're studying engineering systems, it may be that conservation of energy is important. It may be that it's a dissipative system and it's not important. These are things that, the main thing one learns from sort of studying the computational universe, two things that I'm going to, one thing is that there's this sort of infinite supply of, in a sense, innovatively different models for things, which is very useful. The other thing is this phenomenon of computational irreducibility, which has tended to be overlooked because the things that, for example, physics chooses to study are precisely those questions for which computational irreducibility is not very obvious. They're precisely those questions for which we can get the nice solutions, the nice equations, and so on. When there is computational irreducibility, the methods that one's sort of most used to in physics don't work very well. One's reduced to just having to simulate things explicitly. So then the big kind of lesson is, if you're going to have to simulate explicitly, find the very simplest possible model that captures the essence of whatever system you're studying, because that will be the model that you can simulate the furthest and make the most conclusions from. And we should stop here. Thanks.
Thank you very much.
Thanks, John. Thanks, John.
So for members of the press, Stephen will be in the press room for a short press conference. We've got a little addition to the program here. David Alvarado and Jason Sussberg are here. They are independent documentary filmmakers, and they're here to show us a short preview of their next film.
Hey, how you doing? Hi. Just real quick, I wanted to thank the Singularity Summit. This is actually going to be the first time that we're announcing publicly about this film. This is a 3D independent documentary about the science of life extension. Again, this is the first independent 3D film about the science of life extension.
If you're interested in what you see, come find us and talk to us. Also, if you're interested, we have material to distribute, so I hope you enjoy it.
I'm enthusiastic about science fiction, always have been, because it's about the future, the only thing we have left. And when you're growing up in southern Alabama, the future can look very big. That was the era when everything was optimistic. I'm still optimistic. You see, you can't explore an idea without having some imagination. And you can't have a future that you do not first imagine. People are notoriously lousy at anticipating the future. 300 years ago, no one would think men would ever fly through the air. But it's hard to see the future if you're transfixed by the present.
In human history, three really big things have happened so far. Introduction of humans, introduction of farming, introduction of industry.
21. Look down, Jeff. What are you afraid? 7,800 levels.
What could the next big transition be? I teach health economics, and we have a lot of data on how mortality has changed over time. My hope for the future is to not die.
Of course, Methuselah is in the Old Testament. He legendarily lived over 700 years, which we actually believe was something like maybe 70, which was quite rare in the ancient world. The first big improvements were simple hygiene. Then in the 20th century, we got vaccines. In the 21st century, the big thing is going to be genomics. We think that mortality is completely solvable. That implies immortality. A bit over 4 years ago, I co-founded Genesian Corporation. Methuselah flies, our long-lived flies, as we call them, live 4 times longer than the ordinary fly. We realized that if you could read the genomics of these flies, compare them to the control flies, you would extract genes responsible for their ability to live 4 times longer than the control fly. And we did that. It's as though human beings were living to 350 or 400 years old.
Maybe eventually lifespan will increase fast enough that some people will just ride the wave and never die, but we're not in that era now. I don't want to die. I am a Cryonics customer, which means that when something medical severe happens to me, they're supposed to look at this tag and contact my Cryonics provider, and in the worst case, they will freeze me. You just wait until the future is so powerfully smart that they can fix everything that went wrong with you when you died and everything that went wrong with you when they froze you. If cryonics works, think about it, that means that billions of people died needlessly. Stop dying! None of my family, including my wife and children, are scheduled to be frozen. That means if that continues, I won't have any of them with me in this new world. That's sad. I'd rather they were there. But given how unpopular this is, that's my only choice.
The death of my wife was the biggest emotional trauma I've ever gone through. It's not an accident that I founded Genesian 4 years later, because I became more and more interested in the problem of longevity. I should do something about this. Genomics is improving. I'm a scientist. I can understand the arguments. People like me have an obligation. Watching someone you love slowly deteriorate and die really impresses you with how important this issue is. It is the crucial human issue. We're the only animal that knows it will die.
Thank you, David and Jason. That's a perfect transition to our next guest. Our next guest is Jason Silva. He is a writer, a filmmaker, a futurist, originally from Caracas, Venezuela, and now living in Los Angeles. He studied film and philosophy at the University of Miami, where his experimental films about hedonism earned him the nickname the Party Philosopher. After graduating from Miami, he became a producer and a host at former Vice President Al Gore's Emmy-winning cable network, Current TV. He writes at the intersection of philosophy, technology, and biology.